Welcome everyone to the second day of the conference CMMSSP. So now it's time for our first plenary talk, which will be given by Biplab. So I would like to request Professor Orunabha Chakraborty to come to the dais and chair the session. Sir.
Thank you, Shani. A warm welcome again to the second final day of CMMSSP 24. So we begin the day with a plenary talk by Dr. Biplab from Nagaland University. It's kind of a personal pleasure for me to chair this session. Biplab, a brief introduction to the speaker. He graduated and postgraduated from Kolkata University in West Bengal and did his PhD as well there. And after doing his PhD, he went to Max Planck Institute in Dresden, stayed there for a couple of years or so, and then to Ben Gurion in Israel and Tel Aviv as well. I mean, it's a joint project with Amnon Aharani there. And presently, he is working as an assistant professor in Nagaland University in the Northeast. And he works in this area of condensed matter physics, which is a very hot topic these days. So with these few words, I invite Dr. Biplab Pal to give his talk. Biplab, it is a 45-minute talk with 5 minutes of additional time as part of question and answer session.
Okay. Am I audible? Am I audible? Yes, now it's fine. Okay, so hello everyone. A very good morning to all of you. And first of all, I'd like to thank Professor Orunabha Chakraborty and the organizer for inviting me for giving this plenary talk here. And it's a great pleasure and honor for me to be speaking in front of you. And one of the important feature of this conference is that it is basically given by the students, which I really like. And so thank you for inviting me here. So in this presentation, I'll be talking about my works on flat band physics. And as Professor Chakraborty already told you, that this is one of the hot topics nowadays from the perspective of condensed matter physics, optics, as well as material science. And I'll be talking about this particular area of physics from the two perspectives, both theory as well as from the experiment. So, like nowadays, people are proposing different kind of toy models in condensed matter system in theory, and then later on, people are trying to realize those kind of toy models in real life experiments in the field of photonics using optical lattices or photonic lattices. So I have made a few contributions in this direction. And today I'll be showing those toy models and how those models are realized in real life experiments. So before I proceed, no, sir, it is mine. Yeah, okay. So before I proceed, let me highlight my university first, because many of you may not be aware about this Nagaland University. So Nagaland is, as you know, one of the 7 sister states in Northeast, and the distance from Kolkata to Nagaland is about 1300 kilometers. Nowadays, you have a direct flight from Kolkata to Dimapur, but there are other options to reach my campus also, like via Jorhat. So, our university is actually established in 1994, and it is one of the central universities in the Northeast. And we have actually 4 campuses: Lumami, Kohima, Mesdifema, and Dimapur. And the headquarters is basically situated here in this Junegoto district in Lumami village. And basically our science departments and some of these social science department are located here. And this is the headquarters where all the official works are basically done. And I just want to highlight this point also, because our university is one of the vibrant university in terms of offering many courses. Like here you can see a list of some of the top universities which provides many or offer many PG courses. For example, our university offer 81 courses in this PG and also in other categories. So this is briefly about our university. And we have a very beautiful campus here. Here, some of the glimpse of our campus. It is located in a hill area. So the campus is basically This is from Lumami campus because I am situated there. So the campus is basically surrounded by this kind of beautiful hills, and this is basically our physics family. So our physics family is relatively very young. So we started our journey in 2014. So it's like 10 years old department. And this physics family is basically consists of about 60 members. There are 40 PG students, 5 faculties, and there are 12 research scholars in our department. And these are some of the glimpses of the classrooms or the seminar rooms. And this is actually our old building, and we are coming up with this new building, this 4-story building, and we'll be moving to this building maybe end of this year or maybe beginning of this new year, next year. So then we'll have actually a lot of space because our department is relatively small. So nowadays we have this small but nice looking this like a kind of village thing is there, but it's inside. From inside, it looks very modern. You see, this is one of the classrooms, so it is very modern. Okay, so I also like I teach a lot there. So because here we have a lot of undergraduate, postgraduate students, so I would like to give emphasis on some of my teaching activities. So these are some of the undergraduate level courses which I taught previously in my previous teaching position, and then currently I am in charge of teaching these courses in the Nagaland University in these PG courses. And these are some of the screenshot of my teaching materials. And I really I'm passionate about my teaching also, so I put a lot of effort in making these notes. In fact, because I put so much effort in making these notes, so what I do is that I make these notes freely available for anyone to read and use in my webpage. So if you go to my webpage, if you go to the teaching section, you'll find a collection of wide varieties of this kind of notes from different topics, and anyone from any part of the world can freely access these notes. So any students, if you are interested, you can just go through these notes. You may find these notes may be useful for your physics courses. Okay, so now with this brief highlight, let me come to my research works. So these are some of the research areas on which I work. Basically, I am interested in theoretical condensed matter physics, and under this main topic, I'm basically interested on these different kind of subtopics like thin electron states in fractal geometries, then spin-dependent transport and spin filtering effects in certain model magnetic chains, then transport properties in ladder network, which can be used to model and study the electronic properties of DNA chains, because DNA you can model theoretically using this kind of ladder networks. Then localization issues in something called quasi-periodic or aperiodic systems. Then quantum Hall effect. I mean, I have started a little bit of this quantum Hall effect during my postdoc. It was a many-body physics, but then later on I could not continue because of the computational limitation. But I have started over some works on this particular field also, because I was working on fractal and nobody has studied this quantum Hall effect on fractal, so it was a good study there. And then in recent times, I've been interested in this flat band physics in lattice models. So for today's presentation, I chose this particular subtopic where I'll be talking about this flat band physics in lattice models. So this will be the outline of my presentation, because here we have a lot of young students. So I'll start with some basic idea or recapitulate of our textbook knowledge about band theory in solids. Then the question is that what is a flat band and why at all we should be interested in this flat band physics. Then I'll show some of my interesting research results on this flat band physics in some lattice models. And after that, I'll show that how one can experimentally realize this kind of flat band physics in the field of photonics using this photonic lattices. And finally, I'll summarize with some of the concluding remarks from this presentation and what are the future possibilities in this direction. And then finally, I'll just show one slide on the ongoing works. Okay, so please feel free to ask me anything and everything. I'll try my best to answer the questions. And please remember that there is nothing called a stupid question. So you feel free to ask me anything and everything, because a stupid question sometimes lead to a novel idea. So let's get started with these basic ideas. So all of you know that when we talk about this individual atom, there we have this kind of electronic orbits, and for these electrons, we have these discrete energy levels corresponding to this individual atom. Now, when we go to a crystalline solid or in a lattice, there you know that we have a collection of many number of this kind of individual atoms, and in that case, due to hybridization between these electronic orbitals, these discrete energy levels in case of the single atom form this kind of energy band. So this is basically the basic idea about the band theory of solids or the band formation in solids. Now, next thing is that why we study this band structure, because this band structure of any material will tell us about the behavior of that particular material. For example, whether it is a conductor, semiconductor, insulator, that can be identified by looking at the band structure of the system. So this is also one of the very fundamental ideas about this band theory, which we learned during also starting from our school days. And then this is also a very familiar picture from your MSc courses. Whoever have the solid state physics courses, they must be very familiar with this picture. So this is the free electron dispersion relation, and this is the dispersion relation for an electron moving in a periodic solid. This is corresponding to like this block theorem. So these were some of the basic ideas about this band theory of solids from our textbook knowledge. Now the question is that what is the flat band? So suppose if we have certain band structure for a particular material or for that matter any lattice model or any theoretical model, and if we find such a flat line in that band structure, then that is essentially called as a flat band. So this flat band is essentially a flat line in case of a 1D material, and in case of a 2D material, it will be a flat surface with this zero dispersion in each space. And because of this zero dispersion, the group velocity of the particle will automatically become zero, and hence the binding energy of the particle will be quenched, and that's why the particle will be highly localized, particularly at these flat band energies. So these are basically the essential features of any of these flat band states. Now the important question is that why at all we should be interested in this kind of flat band studies. So there are several reasons for studying this kind of flat band physics. So here I'll put some of them. For example, as you have seen in the previous speaker, these flat band states, they offer highly degenerate manifold of these single particle states. And because they are highly degenerate states, so they can be really interesting to study strongly correlated phenomena such as superconductivity or quantum Hall physics or phenomenologism and so on. So this is one of the important things. Then the next thing is that this flat band physics, they can have very useful applications, like real-time applications in the field of photonics, like precise measurement, telecommunication, optical communication, then slow light propagation, enhanced light band interaction, and so on. And then finally, this flat band, if you think about these flat bands, and then many of you may be aware of these Landau levels, which appears in case of a 2D system in presence, in case of a 2D system, in like continuous 2D system, in presence of this magnetic field, we have these flat Landau levels, and these are basically analogous to these flat bands appearing in these kind of discrete lattice models. And these Landau levels are always useful to understand this quantum Hall physics. So whenever we have this kind of flat bands in the case of a lattice model, then those kind of 2D lattice models with these flat bands, they can be really interesting to understand this kind of quantum Hall physics in lattice models. So these are, yeah, so that I'll come because see at the flat band, the light will be basically localized. So that's why we can actually control the speed of the light. So that's why it's called slow light propagation.
You are just flowing the light speed by inserting some medium.
No, that is because of this flat band condition, not because of the medium. Okay, so I'll come to that when I'll talk about this experimental perspective of this flat band. Okay, so in recent times, actually, people are looking for this kind of interesting two-dimensional lattice models, which can host multiple flat bands in their these kind of lattice models. So I have tried to make few contributions towards that direction, which I'll show in the coming slides. Now, if you go to Google and if you search with these keywords flat band in lattice models, then you will find a wide variety of this kind of models which shows this kind of flat band physics. And out of these, all these models, these are actually the two simplest models which shows single flat band in their band structure. So the left one is a Leib lattice model. Maybe some of you are aware about this Leib lattice model because this Leib lattice is studied in different contexts, not only in the context of flat band physics, other different properties, and then maybe Cargo lattice is more familiar to you. So Cargo lattice also shows one flat band in their band structure. So both of these lattices show single flat band in their band structure. Now, in my works, I have tried to find out certain lattice models which can show multiple flat bands in their band structure. So that I'll show in the coming slides. So before proceeding, let me just lay out the general goal about this kind of problems which I do. So what I do, first I try to identify a certain lattice models. Then I write down the Hamiltonian first in Gale space description, and then I go to the momentum space description. Then what I do, I just try to tune the parameters of the Hamiltonian in case test to see that whether that particular lattice model supports any flat band or not. And if those lattice model support flat band, then eventually I try to look for some certain intrinsic properties of those flat bands. For example, topological properties is one of the things which I have studied in this kind of flat band things. And finally, I try to relate this kind of toy models with some experimental things or some possible applications, which people can later on verify experimentally. Okay, so let me start with this example one. So this is basically an extended Gale lattice model. And I'll not actually go into too much mathematical details. In fact, throughout my slides, I'll not be using too many equations. I'll be only showing the pictures because it's good to not to go to these mathematical details. There are a lot of underlying mathematical details behind, but I prefer not to show them because otherwise this becomes more like clumsy for the students. So, but anyway, because of this fast lattice, I'm just showing how this Hamiltonian looks like for this kind of models. So what I do is that this kind of lattice models is basically described by this kind of type binding Hamiltonians, where this first term is basically some kind of on-site term, on-site energy term, and the second term is basically the hopping term. Now, in terms of your PG courses or classical mechanics courses, you can think of this on-site potential to be like this potential energy of the Hamiltonian, and then this hopping part you can think of like the kinetic energy part. So this is in the guideline description, we call as this on-site energy terms, and this is as the hopping terms. So this is the Hamiltonian. Now, in addition to this Hamiltonian, I just want to mention this part will also have an intrinsic spin orbit term in our Hamiltonian, and this will come handy when studying the topological properties for this particular problem. I will explain that why this will come handy when I'll come to the results part. Okay. And this work was done in collaboration with Ankita Bhattacharjee. So she is a postdoc now in Uppsala University in Sweden. So the thing is that now once we get this Hamiltonian in K space, and then immediately using some simple computer program, we can diagonalize this Hamiltonian, and then we can play with this on-site potential and these defined hopping parameters, and we'll immediately find out that we'll have these two flat bands in the system, one appearing at energy E equal to +1 and another appearing at E equal to -1. Okay, just to remind you that here we have alpha equal to 0. That means to begin with, we are not considering this part of the Hamiltonian. So alpha is 0, that means we do not have this part of the Hamiltonian. Okay, so this is with alpha equal to 0, that is in the absence of spin orbit interaction. This is for the bare system. Now, one of the interesting features about this flat band states is that whenever we find out this kind of flat bands, they will be always associated with something called compact localized states. That means this is the kind of K-space description. Now, if you want to understand these flat bands in terms of real space description, so what you do is that you just try to plot the wave function amplitude at defined points at this flat band energies. And then you'll find out this kind of amplitude distribution. So these color sites are the sites where you have non-zero function amplitudes, and as you go beyond these color sites, you have these white sites at the corner. So these are the sites where we have zero function amplitude. So that means that particularly at these flat band energies, we have these highly localized states at this particular amplitude, like CLS configuration or CLS amplitude distribution. So the thing is that at this flat band energy, particles are basically localized on these sides, and as we move away from this side, the wave function amplitude decays to 0, particularly at this energy, not at the other energies, but of course we have other energies in the system where we can have conductive states.
So your question, so in Hamiltonian, this looked like normal hopping term and the on-site term.
Yes.
So what aspect of it gave rise to this flat band?
Yeah, so there are actually many things. So for example, the relation between these hopping parameters also will play a role, and in addition to that, I mean, it will not be automatically happen for any kind of lattices. For example, if you take a graphene lattice, which is a hexagonal structure, so they are automatically not find any flat lattice.
Geometry of the
So yeah, geometry of the lattice will also play a role. For example, if you take a square lattice, so this looks like a square lattice, but in between you have certain sides. So it is like a linear lattice. So if you take a bare square lattice, there will not find any flat patch. But for example, in graphene lattice, also hexagonal lattice, automatically not find any flat band, but then there are certain ways by which even in graphene lattice you can induce this flat bands. For example, if you have a dangling atom in graphene from each of these units still consisting of two sides, if you have an extra dangling atom, then that will give rise to a flat band. But then that you cannot call like a proper graphene structure. Yeah.
But when if you just go back to the Hamiltonian, so if you have such complicated lattice structure, then this you have to go to Fourier space, right?
Yes.
So that's not a problem, is it?
I mean, if the lattice structure is very big, then you will have trouble. But if it suppose this one is just 5 by 5 unit cell, so here you see the unit cell is 5 by 5, so it's not like a very tedious job. But I'll show certain examples where I will have more bigger size lattice structure on unit cell. There it will not be so easy. Oh, this one, yeah. So, like, if the particle hops from say one side to another side, then it will hop back. That means that this harnessing part, the harnessing conductor part, will take care of that. Okay, so yeah. So what I was telling that, so this kind of complex localized states, this we can think of that there the particles are basically localized in this kind of localized prisms. And please mark this picture because this will come handy when I'll talk about this experimental realization of this kind of theoretical model. Please mark this picture. I will again show this picture when we come to that part. Okay, so as I told, one of the things I study for this kind of system is that the topological properties of the system. And to characterize these topological properties, what I do, I try to calculate something called Perry curvature and Chern number. These are something technical terms, but if you want, I can give you an analogous thing which you will understand from your PG courses also. But that, if anyone is interested, I'll talk at the end of my presentation. Okay. So these are some of the standard formulas by which you can calculate this Perry curvature and the Chern number. And if you look at this denominator, you see at the denominator there is a difference of the energies for say nth band and nth band. So one of the key features is that we need to have a band gap between the system. Otherwise, this term will blow up. So we cannot calculate the Perry curvature if we have a band touching. So then, in that case, this effect of this intrinsic spin orbit comes handy. So you see that earlier we had these bands touching with each other, but now suppose if we put a small value of this intrinsic spin orbit term, then you see all the bands are now gapped out, and then you can actually calculate the Perry curvature, and then by integrating the Perry curvature over this case space, you can calculate the Chern number for these different bands. Okay, and you can see that there are certain bands for which you have this non-zero integer values of the Chern numbers, and these are the bands corresponding to certain topological properties. Because whenever you find this kind of non-zero integer values of Chern number, those bands correspond to some topological bands.
But then these bands are not now fully flat, right?
Yeah, no, because you are, this is a good question. So, because now you are putting some kind of perturbation, then you cannot have this. Oh, there is actually a theorem which says that you cannot have simultaneously these three conditions like short range hopping, topological properties, and completely flat band. So, if you have a topological properties of Chern numbers for a particular band, then you need to have some nearly flat band. It cannot be completely flat. Completely flat band will have always zero Chern. Yeah. So that will also come in some of the models I've studied. Okay, so interestingly, now you see that when I tune the value of this alpha, you see on the left-hand side, the values of these Chern numbers, there is a transition. So you see earlier we had certain bands having certain Chern numbers. Now you see this top band and this bottom band are basically picking up the Chern numbers. So you can say that for particularly for this model, there is a hint of topological phase transition from one topological phase to another topological phase, depending on this value of this in-orbit interaction term. Okay, and this bottom panel are basically the plots for the Perry curvature corresponding to these bands, which pick up these non-zero integer values of these Chern numbers.
But for a given material, alpha is fixed, right?
Yeah.
So then how will you have these two states in transit one from the other?
Yeah, so that, see, here what I have done, theoretically it's possible, but then experimentally you need to find out that particular material in which actually you can tune this kind of values of the alpha. Yeah. So you have to model the system. When mathematically in computer I can put any values, it can be very simple, but when it comes to actual these things, it is not so simple. So you have to design the model accordingly. You will find out the right material which can give this kind of values of alpha. Okay, so experimentally this kind of systems can realize this using this kind of waveguide network as well as this optical lattices. This will come in details when I come to the experimental realization of this kind of models. Then let me come to the second example where we have studied the flat band in this kind of diamond octagonal lattice model. Here, this is the unit cell. So this is the diamond placket, and it is basically paired by some kind of external magnetic flux. Now, here the motivation is that we want to study the flat band physics for this absence of this magnetic flux, as well as we want to study the influence of this magnetic flux on the flat band state in this kind of structure. So the prescription is same. We again write down the Hamiltonian, and then we diagonalize the Hamiltonian, and then we play with the parameters of the Hamiltonian, and we see that for this phi equal to 0, that is in absence of this magnetic flux, we have these two flat bands, one appearing as energy equal to -2, one appearing at E equal to 0. And then as we tune the values of this magnetic flux, so for certain value of this magnetic flux, once again, one of the energy, for one of the energies, we have this completely flat band states. And one of the other prescriptions by which you can actually confirm that okay, these states are really flat is that you can calculate their corresponding density of states. So you see that for this particular picture, you have the flat band energy at E equal to -2 and E equal to 0. And as I told in the beginning, that whenever we have this kind of flat band states, they will be corresponding to highly localized states in the density of state spectrum. So you see that corresponding to these energies, we have these sharp spikes in the density of state spectrum. And also for this picture, you see that the flat band is appearing at E equal to -2. And when you study the density of states, you see that exactly at E equal to -2, you have this highly localized flat band state. And once again, as I told previously also, that whenever we have this kind of flat band state, they will be always associated with this formation of this compact localized state. So whenever we have flat band states, in fact, even before going into the band structure, if you take a lattice model and if you can work out this kind of amplitude distribution, then you know that for that particular energy, you will always have a flat band in your system. But it is not so easy how you will get the energy. It is not so trivial. So, but for just if you take a lattice model, then from similar kind of lattice model, you can just guess the energy, and then you can try to draw this kind of amplitude distribution. And by any chance, if you find out that satisfying this kind of compact localized states, then you know that automatically that in your band structure you have that. So it can be other way. Starting from the band structure, you can go there, and also if you find out the compact localized distribution, then you can know that you will have the flat.
Sorry, in that E equal to 0 is special, is it? All are bound states, so aren't energies negative or you have both positive and negative?
No, yeah, so that will be basically depending on this. So energy will be in terms of this hopping. So for example, depending on this hopping and onside potential, you will have the spread of the energy.
So the energy positive bound states, right? You put an energy E, that can be positive. It's not.
No, I did not understand your question. Okay. So for particularly this model also, you see that for certain values of these internal parameters of the Hamiltonian, once again, some of these nearly flat bands, they pick up this nearly, non-trivial, non-zero values of Chern numbers, and this kind of nearly flat bands, like nearly flat topological bands, can be really interesting to study quantum Hall physics. In fact, this trio of these papers by these groups, they have already studied this kind of nearly flat band physics in certain other models like cargo lattice or say checkerboard lattice, and so on. So these are different models in which people have actually studied, and they claim that now they have this quantum Hall physics actually in absence of magnetic field, and this is also featured in this physics viewpoint in this PRL thing. And once again, one can realize this kind of flat bands using this kind of photonic waveguide networks for this particular lattice model. Now, let me come to the third example where I'll be talking about these flat bands for this kind of artificial lattice geometry, two-dimensional lattice geometry. And in this case, what I do is that I take the unit cell of the lattice to be this kind of fractal geometry. And now what I want to do is that I want to understand that as I increase the more and more fractality into these unit cells, how the flat bands span over different energies. So now coming back to your question, so now you see that now if you have this unit cell, then it becomes really complicated. Like it is not so easy to calculate by hand. So, but then there is no option because for this kind of fractals, I had to calculate, like I have to mark each of these lattice points, and then by hand I have to find out the Hamiltonian corresponding what coefficient of the Hamiltonian is 0, where there will be no hopping, and where it will be connected there will be hopping. So for this particular problem, when I go to this higher order generations, then it becomes really complicated.
Are there such materials? I mean,
yeah, of course there are materials. I have some extra slide there, and I can show you.
They are gas.
Yeah, they have gas. People are actually nowadays they are actually experimental synthesizing this kind of fractal. It is very interesting. Yeah. So actually this work is done with in collaboration with Dr. Kush Saha, who is currently a faculty in NISER Bhubaneswar, and he was one of the invited speakers in last year conference of this series. Okay. So now immediately with this L equal to 1 generation, that means with this this generation, with this kind of 6 sides in our system, we immediately find out that we have these multiple flat bands into the system. And then, as I told, I go on to study what will happen as I increase the fractality of the system more and more. So these are for the L equal to 2 and for L equal to 3 generation. And as you can see that as I increase the number of generation of the fractal unit cell, we have more and more flat band in the system. And this is one of the interesting properties which actually comes from the fractal geometry, because fractals are self-similar structure. So like suppose if you get a flat band at certain energy for one generation, that will actually come also in the next generation because of this self-similarity of the fractal structure. For example, suppose if you find here, you see that there is a flat energy at equal to -3, so it is also repeated in L equal to 3 generation. So all these flat band states, it will be also part of this structure, and same as the previous one also. Here you had 0 and 2. This is also part of this structure. Okay, so this is coming because of self-similarity of the structure.
But all these levels are coexisting, right, together.
Yes.
We have drawn them in separate graphs, but they are together at a given time, right?
Yes, yes, sir. Yes. Okay, so in fact, actually we can predict this particularly this formula for a L equal to for any L plus one generation system. So this is a generalized formula which you cannot go to infinite fractal, but you can predict what will be the number of flat bands if you actually go to an infinite fractal. So these are basically the number of flat bands, and these are the number of sites in that particular fractal unit cell, and these are the number of dispersive bands, and they are basically related with this formula with the previous generation. So if you know for a certain lower generation, you can automatically work it out for a very higher generation. So this is the way you can actually do it for a higher generation. And once again, these are the standard prescription. I've already cross-checked this whether these flat bands are really existing by doing this density of state calculation as well as this compact localized states formulation. Okay, and now let me come to this last example where I propose this new lattice model, which is called as Kagome lattice model. So many of you are basically aware of this Kagome, but this Kagome is one of it's my brainchild. I cannot say my brainchild completely, but I studied this flat band on this particular lattice model. No one has studied the flat band on this particular model, but recently this was actually chemically synthesized, and this was published in one of the chemical physics journals. So from that paper, I got this idea, and then I studied the flat band physics. I proposed this flat band physics on this particular lattice model, and luckily this model turns out to be very interesting. Apart from this previous lattice models, I will tell you why. And this is actually done in collaboration with Professor Georges Bauzerer from Lee Institute in France. Okay, as I already told you that you are aware of this Kagome, and then there is also a lattice model which people previously studied. It's called star. Now this Kagome is basically in between the star lattice and the Kagome lattice, and that's why we call this as Kagome lattice. And this is the paper. This is an experimental paper from which I got the idea of this Kagome lattice. Now, once again, what I did, I studied this band structure for this model. So here also we have this flux in these plackets, triangular placket. So for phi equal to 0, immediately we find out that we have a flat band at the bottom of the energy level. Okay. Now, interestingly, now in this case, what happens is that by controlling these values of this flux, you can make any of these bands flat. So that we do not have this privilege in earlier lattices. We have certain bands to be flat, but you cannot make each of these bands to be flat. But now what we have discovered here, that we found out certain special values of this magnetic flux. This is very systematic, and by tuning these values of the flux, you can make any of these bands to be flat. Okay. So next, what I show is that now you see. So in previous picture, we had this bottom band to be flat. Now you see for this particular flux, so this is phi naught by 8. We have the second band to be flat. Then for phi equal to phi naught by 4, we have the third band to be flat. Then the fourth band to be flat for 3 phi naught by 8. And then finally, for phi naught by 2, we can make the top band to be flat. So it's a very nice prescription by which actually allows you to make any of the bands in the system to be flat. And this is like a flat band study is like for a long time, people are studying this, but there is no such report where people have systematically controlled that which band you can make flat. Okay? So this is a very new thing which you have introduced in this particular structure. And
so your earlier pictures, you had flat band without magnetic field, but here you have magnetic.
Yeah, here also in some of the, for example, in the diamond octagon, I showed that it can have flat band both in presence as well as in absence of the flat band. I mean, absence of the magnetic field flux. And here also we showed that both in absence as well as in presence of the magnetic flux, we have the flat band. But interesting is that earlier for certain bands you could make flat, you could not make all the bands to be flat, even for certain values of the flux. Here we found out a clear prescription by which you can make any of the bands to be flat.
Just by changing magnetic field.
By changing magnetic field, and that gives you the privilege that which up to which energy level you want to fill the system. So you have the privilege that okay, I want to fill up to the second level, I want to fill third level, fourth level. Accordingly, you can study this other phenomena like superconductivity, all these things in this kind of structure. So that gives you this more privilege. Okay, and now earlier actually I showed this distribution of the compact localized state, or I always showed for previous lattice structure in absence of this flux. But to do it in presence of this flux is a non-trivial task. And here actually I have shown that these are the corresponding this compact localized state distribution in presence of this flux. And this is actually a very non-trivial task. Yeah, each of this figure actually took me almost 1.5 days because there was no such tailor-made method by which you can do. So I had to try several combinations, and eventually these particular combinations they actually fix. And interestingly, if you see this distribution in terms of this alpha is basically e to the power I theta, and theta actually basically captures this flux. So you see that for each of these figures, the configuration is not the same. For each of these figures, we have a different comment. For example, if you come here, you see that this is alpha to the power 6, but here you see 1, -1, and so on. So it's not the same for all the these things. Okay. And we also checked what happening is the density of states. You see that whenever we have these flat band states, for example, this is for phi equal to 0, we have the bottom band to be flat, then second band to be flat, third band to be flat, fourth band to be flat, and finally for phi equal to phi naught by 2, we have the top band to be flat. And then here also we have studied the Chern number as a function of this magnetic flux, because here what first was to study this flux behavior. So here also you see that there are certain bands for which you get these non-zero integer values of Chern numbers. And then also here also you observe that there is certain value of the flux where you find a transition. So there is also a topological stress transition here. Okay? And these are basically the Berry curvature distribution corresponding to this band number 1, which picks up these positive values of charge number, and then these are for the bottom bands or the fifth bands. These are the corresponding distribution of the charge numbers. Okay. Okay, now I have talked about only about this theoretical model, like the toy models. Now, how people actually can be experimentally realize this kind of models using these photonic lattice platforms. So this is one of the actual experimental studies of these flat band states using this photonic layered lattice. So what they do is that each of these lattice points, which I showed in my theoretical model, in corresponding model, they replace each of these lattice points by this kind of femtosecond laser light retain single mode photonic waveguides. Okay, and then they excite the light at certain of this photonic waveguides, and then they excite light at the flat band condition, and then they observe the intensity of the light in each of these photonic lattice points. And you see that at the flat band condition, here you see that there are only 4 sites where we have these glowing points. That means these are certain points where we have this kind of non-zero wave function amplitude in terms of condensed matter problem. And then otherwise you have this dark spots. That means that light is basically localized at these 4 sites. Now you see that now when they just relax this flat band condition, you see now the light spreads over more number of sites. That means that when you go away from the flat band condition, there is a spreading of light. That means that the flat band is basically broken. Okay? And yeah, so this work is actually driven by Shiobroto Mukherjee. He is one of the experts in this kind of photonic layer lattice. And then the similar work was also done also in this same edition in this physical review later. And this was basically driven by Rodrigo Vicencio. Where he has also studied this flat band in this photonic layer lattice model. Okay? And this is how they actually experimentally grow this kind of lattice structure. This is real-time picture taken from their paper. I mean, I think it is from the paper of the Rodrigo Vicencio. And this is the whole like typical their laser setup looks like, the experimental setup for studying this kind of flat band physics. And then actually the list goes on for a wide variety of lattice structures like rhombic lattice, sawtooth lattice, Kagome lattice, and so on. So it shows that this kind of flat band physics can be realized in experiment as well. They are not just toy models. Okay. And more interestingly, in recent times, people have actually come up with this kind of metal organic framework, which also shows this kind of interesting flat bands in their structure. And this shows that this flat band physics nowadays also becoming interesting from the perspective of material science as well as from the sort of chemistry, because these are some of the journals you can see that they are also like these nanoscales. Mostly people are publishing chemistry or material science. People are publishing in these journals. Okay. So now in the last part, I'll just try to show you that all these models I talked about, my models, these fancy models, are they only good on paper? And the answer is no. Each of these models actually have been realized in experiment following my proposition in these theory papers. Okay. So let me start with this example 1. If you remember, the example 1, I talked about this external layer lattice. So in their paper, instead of calling it external layer lattice, they call it as decorated layer lattice. And now you see that they have experimentally grown this external layer lattice, and they have actually studied this flat band physics in terms of photonics. Okay. So now you see that I showed this. I told you, if you remember that, please mark this picture about this compact localized distribution. So you see that corresponding to exactly my proposal, they have actually found out this amplitude distribution in terms of this intensity of light, and these are the glowing points corresponding to the sites where we have non-zero wave function amplitudes, and these dark sites are basically the sites where they have zero wave function amplitudes, and the light are basically localized under the flat band condition on these sites. And once again, I'm coming to this picture. You see, these are the red sites and these green sites. And in their picture, they have used this red and blue, and these are the corresponding these things where we have these glowing sites corresponding this non-zero function amplitude. So this was the first example I talked about. Then in the second example, I proposed this diamond octagonal lattice model, and this has also been experimentally verified by the group of Rodrigo Vicencio in his physical rule A paper, but they have experimentally studied this flat band physics using this kind of photonic lattice setup. Okay, and in the third example, I talked about this proposal about realizing this flat band physics in this kind of fractal-like geometry, and this has actually realized by two groups. First, by the group of Zizan Chang, and they have published this paper in April Photonics, where they have exactly studied this model which I proposed, and they have studied in terms of optics, and they have found out this kind of amplitude distribution in optics corresponding to these flat band states. Then also the group of collinear Danes, they have also studied in recent times similar kind of physics in this kind of photonic fractal-like structure. Okay, and the last one, as I told, this is actually other way. I took the idea from their paper, but nothing has been done on this flat band physics. But maybe following my paper, later on people may try to realize this structure also in the field of photonics. Okay, so it shows that these toy models which I have studied, basically they're not just mere toy models, but each of these models have been experimentally realized by the community. Okay, so now let me conclude. So what I have shown here is that, like using simple mathematical tools, you can propose certain intrinsic lattice models which host multiple flat bands in their band structure. And then what I have shown that, suppose by introducing certain kind of perturbation, like for example magnetic flux or spin-over interaction, we have studied some kind of topological properties of this kind of flat band models, and then this kind of topological properties can be really useful for further study of something called charge insulator or quantum Hall physics. And lastly, I have shown that this kind of flat band physics can be experimentally captured using this kind of single mode photonic waveguide networks. Okay. So these are some of the future like outlooks which one can look into. These are some of the open questions. Like for example, what will happen if you introduce some kind of disorder into the system or interaction? Then whether one can find out some generalized scheme by which you can tell us that okay, for this particular lattice model we have this number of flat bands, for this particular lattice we have this number of flat bands, and so on. And finally, all these models I have studied for spin half electronic systems, but is there a possibility that can we think of proposing something called for higher order spin systems, like with spin 1 particle? Can we study the flat band physics for spin 1 or spin 3/2 particles? And then finally, this is also a very interesting area. Like all these Hamiltonians I took, they're all are Hermitian Hamiltonian. But if you try to introduce some kind of non-Hermicity into the system, what will happen to these flat bands? Okay, so here I basically discussed these 4 papers. Okay, so all these 3 papers are already published in PRB, and this is actually under review in PRB. So paper report has also come, and it's really positive. So I hope that within a few days it will also publish in PRB. Okay. And these are actually 2 ongoing works. So now actually interesting fact is that I can, maybe in 1 year time I can tell you more about these experimental things, because I started collaborating with this guy, Rodrigo Vicencio, who is one of the experts in this, doing this kind of photonic lattice things. But here actually we are not studying flat bands, we are studying something other thing. We are trying to study this Erno-Bohm caging and galactic transport in this kind of model systems. What I have done is that I have done theory, and then he is now implementing my theory in real life experiment, and the signal is positive. He has already realized this theory proposed by me in the experiment, but he has to finalize the lattice size so that he get the best result for that particular lattice size. Okay, and this is another, like, I'm about to start this work once again with George. So here I plan to study this flat band superconductivity. It will be a new thing for me because I was proposing the superconductivity, but I have not studied because I'm not an expert in superconductivity, but he is an expert on superconductivity. So we're trying to propose this idea of studying this flat band superconductivity in this kind of nanostructure of fractalized models. So with this, I've come to the end of my presentation, and I thank you for your attention.
Thank you, Biplab, for a very nice talk. I now yes, Biplab.
On top of the flatness of the band just by calculating the density of states.
So this is an immediate or immediate calculation. Is there any direct measurement of conductivity so that conductivity will vanish for that?
No, I have not actually studied the transport properties, but then there is another way. I mean, in numerical, what you can do, you can study, I mean, you can calculate something called flatness ratio. Okay, so flatness ratio will be, so for example, if you take a particular flat band, so that is the bandwidth, and then divided by the gap to its nearest this dispersive band. So like that will give you this flatness ratio, and that will tell you how flat that particular flat band is. For example, when I talk about this nearly flat band, then what people try to understand is that how flat those are by calculating the flatness ratio. In fact, for some of the studies, I have also calculated the flatness ratio, but here I am not showing it, but that is in my paper. So flatness ratio, I have talked about the flatness ratio, but in terms of conductivity or this transport, I have not calculated because yeah, one can do that, but I have not studied that. But because for the particularly flat band, you will always get a zero conductivity because they will be highly localized, so there will be no conductivity. Yes, yes.
Any other questions? So,
So firstly, I would like to thank you for your nice picture and discussion. My question is, what are the limitations or what are the challenges associated with flatband in real world application like imperfection, material, or interacting into the devices? What are the challenges or
So I mean, suppose the models I propose, you see that they are mostly realized in this kind of optical setup, because in optical setup or photonic setup, what happens is that they are like a very clean system. So there is no interaction there. So they are actually, you can study these properties in a very tunable way or in a very flexible way by controlling these internal parameters. But if you talk about this real material and synthesized in laboratory, then when condensed matter or solid state materials, then all this interaction, all these things will come into play, and then the realization of this perfectly flat bands or say, for example, nearly flat band will not that be so easy. Okay, because that's why that is one of the reasons people take this kind of optical lattices or photon lattices. So that is one of the questions Professor Chakraborty asked yesterday to one of the participants that why people propose these optical lattices or photon lattices to realize this condensed matter theory, because in optical lattice or photon lattices, they are very clean systems. So there is no interaction. So you can study this non-interactive physics in a very nice way there. That is one of the reasons.
Like physics are real, right? Compared to actual crystal optical lattice.
Yes, yeah. Optical lattice actually is of the order of micrometer. Micrometer.
But then we're talking about, I mean, what is the relevance of that in optical?
So yeah, I see. I cannot go deep into this, so I can just tell you on the surface. What is happening is that suppose when you talk about superconductivity, is that the electrons form the Cooper pair. Now, suppose the electrons are made to sit in a suppose they are made to sit in this particularly flat band states where you have this high degeneracy. So whenever you have the high degeneracy, that means that you have only one chair to sit and you have many states to sit in the system. So automatically there is a strong correlation among these particles. So that is how they can be connected with the superconductor physics. And there is actually recently I learned from George that there is another way. For example, what we're trying to calculate is that this Bailey curvature. Actually, the span of this CLS, they will also measure that how good a superconductivity can be in that particular lattice system or not. So if it is spreading over long systems, that is an indication that okay, this system may support superconductivity. So that is one indication.
Another question. Okay, I will take this question and then of course we have
the theory part you mentioned about you mentioned about an empirical formula regarding the number of lattice cycles.
Yeah.
So when was such thing proposed? When was that formula being proposed?
No, that was done. That was done by me. Nobody has proposed. I have done that. Yeah, empirically. Suppose
How old it is? Just to know.
that was published in 2018. Yeah. But these experiments have been done recently, like 2020 or 2021, 2022.
last one we discussed in experimental slides, you mentioned about metal organic framework. What is the reason behind using such framework?
Yeah, so that is like what is happening is that like people can chemically synthesize this kind of materials in real time. That is the one of the way that okay, they cannot do it for a particular solid system, but using this kind of chemical molecule, they can do it. And another way is that they can do those things by also by proposing theoretically by using DFT. So in DFT, they have this tailor-made code where they actually can plug this kind of systems, and then they have really all can put all this interaction, all these things into the system, and they can have these pictures from DSP study that they have this band structure, and they are also they can find out these characteristics. Yeah. So, sir, coming to your thing, so you see these are actually chemically synthesized these fractal structures. People have actually chemically synthesized. This is one of the recent papers where they have synthesizing. This is a real time all the levels. Yeah, 2D. Yeah, 2D is, I mean, if you talk about geometry is 2D, but then fractal, they have a fraction.
Euclidean dimension is
Physical dimension is 2D. Yeah, but if you talk about, so this is another example. So they have chemical, like they have taken this kind of structures and then they have self-assembled this structure to grow this kind of self-assembled fractal structure. So they are not just like kind of designs. They can people can nowadays actually make this kind of structures.
okay. I think many of you will have many questions. People will be available here for all the sessions. So let us again thank Dr. Ikra. For this stage, we have our student Shaun who will be giving you a memento. And then here it is.
So actually in the introduction, Professor Chakraborty mentioned so many things, but one thing he cleverly passed is that like when he talked about he did his MSc and PhD from the University of Poland, but he did not mention that you are my supervisor. Really cleverly passed. That's true. আমি আজকে তুমি লাঞ্চ ডিস করতে পারো তারপরে আমি চলে যাচ্ছি ঠিক আছে থ্যাংক ইউ এটা এবার লাগিয়ে এটা লাগিয়ে নাও এটা তো জানো ঠিক আছে কোনো সময় কিন্তু লাঞ্চের পর আমি চলে যাচ্ছি শিখলাম একটু So actually, this fractal system history people have really started to be interested in the fractal.
Hello, hello. আচ্ছা 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 প্রেজেন্টিং বাকুল ওই দেখি ঠিক দেখে ও এটা দেখো
Thank you, Dr. Pal and Professor Chakraborty. Now it's time for the first oral presentation. So thank you, Dr. Pal and Professor Chakraborty. So now it's time for the first oral presentation session of day 2. So this session will be chaired by Ishika Mandal, UG third year student of Department of Physics, Presidency University. So Ishika, start this.
Well, thank you, Shabni, and good morning to all of you. I am Ishika, Welcome to the third oral presentation session of our two-day national conference. A gentle reminder, every talk will be of 13 minutes followed by a 2-minute quick question answer session. I shall give you a warning after 10 minutes. To the audience, I would request you not to interrupt during the presentation or during the talk. Please save your question and your queries for the designated question answer session. With that, let's proceed to our first speaker, Debabrata Chini, a master student from Vidyasagar University. I would like to call him on stage. I'm very sorry. Each talk will be of 12 minutes, followed by a 2-minute quick question answer session. Sir.
এটাকে আমি চেঞ্জ করবেন না, আমি জাস্ট এখানে চেঞ্জ করুন আর এইটা দিয়ে পয়েন্ট। ঠিক আছে, ওকে, ঠিক আছে, ঠিক। Firstly, I would like to thank you, the organizers, for giving me this opportunity to emphasize my work. I just did this work in Inspire project under the supervisor of Professor Novinder Singh in Physical Research Laboratory, Ahmedabad. My title of this project is The Dynamics of Electron-Phonon Interaction in Non-Equilibrium Conditions, a two-temperature model approach. Next, my aim and objectives are the dynamics of electron-phonon interaction under non-equilibrium conditions play pivotal roles in understanding energy transfer process in quantum matter physics. The study employs the two-temperature model (TTM) to investigate the relaxation mechanism and temporal evolution of electron and phonon subsystems following ultra-fast excitation. By coupling the electron and phonon temperature equation, we analyze the energy exchange rate and relaxation time scale that characterize non-equilibrium states. Our results provide insight into the transient thermal behavior and the influence of material parameters on the interaction dynamics. This research advances the theoretical framework for non-equilibrium thermodynamics and has significant implication for the design of material in optoelectronics and thermal management applications. Next, the introduction of this topic is that the dynamics of electron-phonon interaction in non-equilibrium conditions are critical for understanding energy relaxation process in various materials like In this TTM model, effectively describe the dynamics by considering separate temperature for electron and lattice, that is basically the phonons. The model involves solving two coupled equations, coupled differential equation, like one for electron temperature T and other for TL for lattice. These equations are given in these two, where C and Cl are heat capacity of electron and lattice respectively, and G is the electron phonon coupling constant, and Pt represents an external energy source. This model is pivotal in material science for tailoring optoelectronic properties. Next, thermal framework of this topic. The TTM model provides a thermal framework for describing the non-equilibrium dynamics of electron-phonon interaction by using separate temperature equation for electrons and phonons. It effectively captures the energy exchange mechanism essential for understanding material properties. Like in this diagram, I like to describe that excited metal consists of interacting subsystems, like first non-thermal, where non-Fermi-Dirac electron component transfer by considering the scheme model. Next, phonon bath after final using the classical BBP equation, like Boltzmann-Bloch-Peril's kinetic equation, final outcome for Fermi component. And after that, the methodology that I followed, first we derive the Boltzmann-Bloch-Peril's kinetic equation. Next, calculating the transition state using Fermi-Golden rule, we derive the phonon generation rate. Thirdly, after that, by solving the delta function, we deduce the electron to phonon energy transfer rate. After, we make two approximation of high temperature, where T greater H plus omega by kV, and for low temperature. Finally, we calculate the electron to phonon energy transfer rate with respect to electron and phonon temperature. And the result outcome, by plotting the Python script, we plot a graph, the energy transfer rate versus temperature of electron and phonon respectively. The analysis and interpretation of this project is that the analysis involves solving these two coupled equations of electron and phonon temperature. Interpreting focuses on understanding the energy transfer rate, the impact of electron phonon coupling strength, and the role of external energy sources in drawing non-equilibrium conditions, where are the crucial for optimizing material performance in optoelectronic and optophotonic application. In given the ray diagram, scattering of an electron from a surface where incident electron is incident at this metal to semiconductor surface, and after scatter we get scattered photon direction. And here I am not describe the mathematical derivation derively, but the mathematical derivation outcome is that using this Fermi-Golden rule, where the transition between the K2 K state, the probability per unit time is given by this equation, and after we assume the energy transfer rate is given by this, where U is the energy transfer rate per unit volume, and NF dot the number of electron and phonon transitions after unit time. And thirdly, we interrupt here the classical Boltzmann-Bloch-Peril's kinetic equation, and using this three equation, we now finally substitute this equation in equation 2, and we finally get the equation 4 is in terms of energy transfer rate from electron to phonon transition is given by this equation. And finally, last, we approximate two temperature. One is for high temperature, T greater H cross omega by kV, and low temperature approximation where T less than H cross omega by kV. And using these two equations, we now get the final equation of energy transfer rate of transition from electron to phonon. And after solving these equations, we get the final conclusion is that an important point to be noted in the above equation is that the electron to phonon energy transfer rate depend the fourth power of electron and phonon temperature as compared to the corresponding case where in the bulk it depends upon the fifth power. And after analyzing these two approximations for low and high, we finally get that for low temperature, it becomes polynomial equations like U proportional to T to the power 5. And for high temperature approximation, we get the linear characteristic curve in U versus T. And after the two temperature model effectively captures the dynamics of electron phonon interaction under non-equilibrium conditions, providing crucial insight into energy relaxation process in materials. Our study understood the importance of electron phonon coupling strength and external energy resources in influencing these dynamics. Future should focus on reflecting the model to take into account the complex interactions such as electron phonon and phonon phonon coupling and exceeding this framework in low dimensional materials, and additionally experimental validation using advanced technique where we enhance this model accurately. Such advances will contribute signify to development the materials with optoelectronic properties for topological and technological applications. And final result is achieved for low dimensional case. It becomes the linear characteristic of this curve, and for the high temperatures where H cross omega greater TV, we here use the classically Debye model theory. And for the high temperature where T greater H cross omega by kV, it looks like the proportional to T to the power 5. And finally, we choose some references by this professor and his research paper. I just conclude here the two temperature model of non-equilibrium electron relaxation and odd electron relaxation in the metal nanoparticle dissipative electron phonon system, and which five and some reference book in quantum mechanics and condensed matter physics as well as statistical mechanics. I just conclude for derivating this final outcome. And lastly, I declare that the details fact mentioned above are true to the best of my knowledge, and I solely be held responsible in case of my discrepancies found in the details mentioned above. Thank you very much for the organization and the organizers to giving me this opportunity to explore my short project work. Thank you very much.
Thank you so much. Now we're open to take the questions.
No, sir. I just do my DST Inspire project in my MSc course. Yes, sir.
These two conditions, linear and per 5. Has it been seen in experiments?
Yes, sir. I said I already understand your question, but this is my theoretically derived. But I think this app is also after predicting this theoretical framework, he also perform experiment in his lab. But I don't, I don't know about the experimental outcome of this result.
Actually, I'm asking one. How good is this temperature approximation?
Yes, so this is just assume just in classical DY model, we just approximate the classical low temperature approximation and high temperature approximation. Thus, these two approximation is already made here.
No, but I was saying I feel the solution that you perform this. As far as I'm
He is also theoretical physicist. You just tell no, he does not do experiment, but in his lab, he does this theoretical framework to each other experimental condensed matter physicist to predict this topic is good, uh, this experimentally is valid or not. Basically.
Thank you, Mr. Chini. Now we have Dr. Sujoy Dotto from KNM High School, Kolkata. I would like to call him on stage.
Slideshow. দেখেন নাইস আচ্ছা এটা কি এটা তো এটা তো হচ্ছে না এটা
Hello everyone. I am going to talk about the importance of proper exchange correlation functionals in material science research for environmental remedies. First of all, I will talk about the motivation of material science research for environmental remedies and its different branches. Then I will try to say something about the theoretical schemes to identify perfect photocatalytic semiconductors. And finally, I will say something about the examples of photocatalytic materials and other environmental materials. This is the art as we have seen in the year 2000, and this is the condition in 2020. What we have done? We have done a lot of deforestation throughout these years, and we are facing the problem for that. The environment is now taking the toll, and that's why we are getting so much environmental massacres, floods. We are getting 38 degrees in Alps itself. So it is not very late. People have started thinking on that matter, and they have started working on that. Material physicists are no way behind. These are different fields where material physicists are now working on. These some are working on different photocatalytic materials, solar cell materials, battery materials, and few are working on this type of materials where they are trying to capture the noises. Other fields are there. I am not going into details. So why photocatalysis is in discussion always? Because through photocatalysis, we can degrade the pollutants. We can capture carbon dioxide to make hydrocarbon fuels. We can split water into hydrogen and oxygen, where hydrogen can be used as fuel and oxygen is always good for us. So photocatalytic research is now gaining popularity. This is how a typical photocatalytic research, a photocatalytic reaction uh, occurs. The
reduction reaction occurs at conduction band, whereas the oxidation occurs at valence band. And for that, we need a semiconductor with a certain gap. These are the thumb rules. These are the thumb rules for finding a good photocatalytic material. The band gap should be greater than a certain value. Always the position, the alignment of valence band maxima and conduction band minima should satisfy some thing such that the conduction band should be more negative than the hydrogen production level, and valence band should be more positive than water oxidation level. As a material physicist, what we do theoretically, we try to find the semiconductor band gaps accurately. We try to find the band alignments accurately, and also we try to find the optical absorption in a good way, so that we can say that this material is good for photocatalysis or not. In theoretical scheme, most of the people who works on these things, they do density functional theoretical thing, and in density functional theory, we actually solve the quenching equation. This is a transcendental equation where both sides are dependent on the wave function, and so it should be solved iteratively. The problem is this effective potential part has a term that is called exchange correlation potential, which cannot be explicitly known. There is no function no defined for this one. And for that, there are several labels of approximations. The easiest way is the local density approximation, where the exchange correlation energy depends solely on the local electron density. Then comes generalized gradient approximation, then meta GGA. All these three types of thing are compiled in semi-local type exchange correlation functionals. There are different higher orders where the hybrid functionals or the RPA comes in play. As we climb up, we get better accuracy, but the problem is that it becomes computationally very challenging for these two steps. So people try to find something within this regime, so that they can be used to find to calculate the semiconductor properties properly. Problem is the non-empirical functionals, exchange correlated functionals, are not well performing in finding the band gas actually. So people try to try to produce some semi-empirical things. One of the most popular prescription for that given by Sevin and Gons, where they said that uh, if the asymptotic potential can be reproduced exactly by any exchange correlation potential, then we will get good band gaps. This is the exact type potential, exact type asymptotic potential with the schemes. And within our scheme of VLB full potential NMTO, we could produce these kings accurately for textbook semiconductors. Then we go further to use those things on photocatalytic materials. Carbon nitrates are well known for photocatalytic applications. Among the graphitic phases, these are triazine type and these are heptazine types. And we have calculated the band gaps using our VLB and HEC hybrid functional. As we can see, those values are quite matching with the experimental results. So we can rely on them. Also, we find this gamma phase as a good thing. I am not going into details of gamma phase here. Next thing, what we should think that we can produce electron hole combination, but there is a chance for recombining. So the mobility of those electrons and holes should be higher so that they don't recombine, and for that we need a low effective mass. These are the calculated values of effective mass for these materials, and for these graphitic phases, this TG AB and AG phases. These values are quite good. In the next step, we found that the valence band maxima and the conduction band minima is also satisfying the condition that we have told earlier, and thus we could say that these graphitic phases as well as the gamma phases with 110 planes illuminated are good for photocatalytic application. But is it that straightforward? If we are getting good result with HKC or VLB, then we are just going to say that this is the ultimate thing? No. There are certain materials like titanium oxide, MnO2 or zinc oxide. Those are used for environmental remedies in photocatalysis or many other fields. Those are made by these are actually transition metal oxides, and for those highly correlated materials, you have to incorporate this Hubbard term within the Hamiltonian so that we get a good result. This is a relatively new work by us. This is actually a combined work of with experimentalists where we have shown that this cobalt alpha MnO2 is giving good good electromagnetic interference shielding behavior. Electromagnetic interference shielding is needed for very sensitive electronic materials so that the noise don't spoil the game of those materials, those devices. Uh, so finally, we can say that for environmental remedies, new materials are important. People are working on that. And DFT as a theoretical tool is good for that. And for DFT calculation, we have to be very serious about the choice of exchange correlation functionals. I know the time is taking. Time is taking for this talk. Time is taking for us to think about our environment. We should work together to make our planet better. Thank you, everyone. Thank you for listening. If you have any question, please feel free to ask. Yeah. This VLB potential was already there for atoms and molecules. I incorporated this VLB within the full potential in order affinity orbital package to use it on solid materials. So how many atoms you know? For carbon nitrides, the the largest cell I have taken was around 28 atoms of like that. So, I mean, we are able to use 28 atoms using other skin. Yes. Right. Honestly, even more than that. Yeah. As for quantum espresso or good quantum. Yes.
Why you chose the C3 info? What is the
This is a hot topic actually. Carbon nitrides are now in discussion because of their photocatalytic performance. And it doesn't have any metal, so it is a metal free photocatalytic, pure photocatalytic materials. So it is no nothing harmful in it, right? When we are talking about anything with heavy metals, there is a chance that the heavy metal came back to the environment. What we are going to do better with this material do harm to the
You say that is environment.
environment.
And one is called graphic.
Graphitic means these are layered materials like those carbon nitrides are in a plane, and then there is a separation between these planes. That's why.
So it's like how you structure the layer. It has nothing to do with graphing.
No. It has graphitic structure. That is layered structure. Nothing else. It has nothing to do with graphene or something. These are already synthesized in many labs, already in use in photocatalysis.
So the clarity what that Howard term actually.
Howard is used for strongly correlated materials, specifically because in density functional theory, when we are doing using those exchange correlation function, we cannot uh, properly address the ID correlations between those electrons in transition metals. So we have to put this Hubbard term by hand. But in this work, this is not put by hand. It was calculated with self-consistently using quantum expressor actually. Mercury group.
When must this Howard term first being thought of?
Howard
I have no historical. I guess 98. Thank you.
Any other question? Thank you, everyone.
Thank you, Dr. Sujal Datta. Our next speaker is Devanshu Shekhar, a PhD student from IIT Kharagpur. I would like to call him on stage. Navigations. That means with this, you wait from here.
This one what?
No, that is only for pointing the laser, and here you have to do the rest of the steps. So, this one here. This one.
First going. Thank you.
Okay, so let me first begin by thanking the organizers because this is the first time I have been given an opportunity to speak at a conference. And I would also like to thank Dr. Biplab Pal for his very interesting talk. Because before this day, I had no idea about flat bands, but now I do. And also, yeah, but I don't work on flat bands. Okay, so also, at the onset, I would like to apologize for all the mathematics I have put in because I cannot avoid it because my work is very mathematical, also numerical. So this work is about entanglement dynamics of many body systems with evolving system conditions. And this has been done under the supervision of Professor Pragya Shukla. And so let me begin by first giving an overview of my talk. So let us consider this Hamiltonian, which is a random field Heisenberg model. And this is nothing but a interacting spin model, which with an on-site random field, which is random. And here I consider in my work the the magnetic field to be not Gaussian distributed with some mean zero and variance h. Now this system has a peculiarity that as you tune the interaction, the disorder strength from some zero to some value h, there comes a point where it shows a phase transition from the thermalized to a localized phase. In other words, it also means that it shows a transition from a Wigner statistics to a Poissonian statistics. Now we solve this system for several system sizes, and we use quantities like quantum entanglement and spacing ratio to characterize the phase transition. Now the main contribution of this work is to formulate a random matrix treatment of this system, and in doing so, we also obtain a single parametric formulation for the evolution of the properties of the system. So let me begin by motivating how the matrix elements of a system becomes random. So consider this Hamiltonian, which is nothing but a chain of particles, charged particles, which are interacting electromagnetically. Now, in any product basis, if we try to calculate its matrix elements, so this term is order n square, and it is not possible to calculate this exactly, and so we resort to approximate techniques, for example, numerical techniques to evaluate this integral, and thus, in this case, deterministic limitations would lead to randomness because we can only know the matrix element up to an error. Another model is that another case where randomness can appear is, for example, this Anderson Hamiltonian, where you have an on-site disorder uh, in the system, and because of this, only the so since it is on on-site disorder, the diagonal elements of the system will be random. However, since the hopping potential Vij are non-random, they can be determined exactly. So the point I'm trying to make is that a Hamiltonian can have both random and non-random components in general, and their distribution will be in general system dependent and also multi-parametric. Multi-parametric because they will be dependent upon the system specifics. If we choose the elements to be Gaussian distributed, then in general their joint distribution can be written like this. So where mu is the mean and b is the variance of each of the elements, and in general they can all be different. So the schematic of the variance distribution in the matrix will look like this, where the color represents the variance of each of the elements. As you can see, all of them can be in general different. And here it runs from 0 to 1, where 0 corresponds to that they are not random. Okay. Now, since I am interested in the changing system conditions, so it turns out that the joint distribution also evolves as the system conditions are changed, and that can be mapped to a Fokker-Planck equation like this, where y on the left hand side is given by this, which is a function of the distribution parameters, that is the means and the variances here. Okay, so let me emphasize upon this equation a little bit more. So what I'm saying is that, so in your system, you can have many different parameters which will affect the mean and variances of the matrix elements, but you can map it all to a single parameter y, and you can thus study what we call as a single parametric formulation. The same thing is also depicted here pictorially. Now, since we are interested in the entanglement, it is imperative that we understand how the eigenfunctions evolve. So if you look at the eigenvalue equation, HU lambda u, where u is the eigenfunction. So in this paper, this is a work of this paper that we can write down the diffusion, the evolution equation for the eigenfunction components, where this parameter lambda e is related to the parameter y defined earlier, scaled by the local mean density. And we choose the following definition for the local mean density because it gives us the best result. Here, delta E is the local mean spacing, and Y0 corresponds to some initial condition which we have in the system. Now, this is all the work which has been done by my professor, but I have applied all this formalism to calculate the entanglement. Now, if we talk about the bipartite entanglement, what we have is a chain of, let's say, 10 particles, and we now calculate the entanglement between half of them. So half of them will fit in system A, and another half form the system B, and then we want to calculate the bipartite entanglement. Now, in order to do that, what we do is we write down each of the eigenfunction in a bipartite basis, and this amounts to writing the column vector of the eigenfunctions into a matrix form, which we call the C matrix. Now, once we have the C matrix, we can calculate something called the reduced density matrix, which is the single most important quantity to quantify the bipartite entanglement of pure states. And using the evolution equation for the eigenfunction, we can calculate the evolution equation for the joint distribution of its eigenvalues, which are also called the Schmidt eigenvalues. Now, once we have this, the evolution of the joint distribution of Schmidt eigenvalues, we can calculate the entanglement entropies because they are the functions of these eigenvalues. Now we come back to this model. So in this model, we have an on-site disorder. So just like the Anderson Hamiltonian, only the diagonal elements will be random. So the matrix structure looks something like this in the basis where the total spin is 0. And all the off-diagonal elements will be non-random. In fact, most of them are 0. And so this is a very highly sparse matrix. So if you write down the joint distribution of this Hamiltonian, it turns out to be like this, where the diagonal elements are distributed with some mean mu and variance b, where b is given by this, and mu is some function of the parameter delta and the system size. The off-diagonal elements here are, since they are constant and non-random, are approximated by a Gaussian distribution with a vanishing variance, and the mean j by 2 because they are all equal to j by 2. Now, following the prescription I described previously, we can calculate the parameter y with a Poissonian initial condition, and from y we can calculate the parameter lambda e. The mean spacing we calculate numerically. So first we calculate the linear entropy, which is a quantifier of entanglement, which is 1 minus the purity of the reduced density matrix, and it goes from 0 to 1 minus 1 by Na, where Na is the Hilbert space dimension of subsystem A, and 0 corresponds to a localized state, and the maximum value corresponds to thermalized states. So here are the results. So on the left hand side, what you see is the I have plotted the linear entropy with respect to the disorder strength H, and on the right I have plotted with respect to lambda E. So what we see is that we get a very good collapse of the entropy with respect for various system sizes. Now in between somewhere here we see some sort of phase transition. It is supposed to show. So and the fluctuations of entanglement entropies are used as a proxy to determine the phase transition. So we also study the variance of the entropy, and at some point in between here it diverges, and that's what we think we can call the phase transition point. And so to compute analytically everything, we start from the same the equation which I showed earlier, and we know the definition from the purity, which is sum of lambda and squares, and then we differentiate both the sides, and we put in the above equation here, and then by doing repeated integration by parts, we can get the evolution equation for purity and then for the linear entropy. Sorry? Oh, okay. I'm almost finished. Yeah, so this is the final equation which we get for the average value of purity and also for the variance. So we plot this equation and we see that the theory and numerics are close. So to summarize, what we have shown here is that a random matrix treatment of a complex system can in general will be system dependent and also multi-parametric. Nevertheless, a single parameter lambda e can be formulated to govern the dynamics. The system specific details will only appear through the parameter lambda e, and we use this formalism to analytically to calculate analytically and numerically the entanglement entropies in terms of this parameter, and we apply this formalism for the many body localization transition in the one-dimension random field Heisenberg model. So these are some references. Thank you very much for your attention.
Thank you. Any questions?
How do you arrive at that row of H that you showed at the towards the last?
Row towards the last.
Yeah, this.
Oh, okay.
Yeah, this one.
Yeah. So we can calculate. So we can actually we can calculate that the variance of the elements which are random are h square L by 4, because there is only on-site disorder for all the L sites. So variance will scale as h square by 4 times L, and mean we don't know. Mean we cannot exactly calculate because we just know it's a function of delta and L, but finally we found that it does not play a role in this parameter which we want to calculate. And the variance, and the off-diagonal elements, they are all non-random because they come from this term and they are j by 2. So it's a Gaussian distribution. We have approximated it as a Gaussian distribution with a vanishing variance, because if the width is small, it means that it is not random. It's a constant.
That's where the approximation goes in.
Yeah. So we limit the BKL going to 0. So that's a power of this formalism, that even it can handle non-random and random both the components. You just have to set the variance to 0.
For the characterization of these transitions of this transition,
Yeah.
is this I mean, there must be other ways of characterizing it.
Yeah, definitely. There. So you can also calculate. So I have also calculated spacing ratio and like level statistics, but my main work interest in entanglement, so I have focused only on the.
Why this? Is this more powerful or?
So, like powerful in the sense that I just wanted to test this formalism on this model, this formalism of single parameter formalism. Because if you know, if you have some picture like this and you want to make them collapse on top of each other, you would use something like the finite size scaling analysis. But what I've shown is here is that if you take a random matrix treatment, that is not required.
So I have a question that here you have taken this diagonal disorder.
Yes.
Do you have any idea what will happen if we take off-diagonal disorder?
No, I just took this model because it's very popular and it shows this kind of.
That like people have taken this off-diagonal disorder
No, I am not aware of it.
because it is numerically challenging or
Yes, I think so because what is good about this model is that it has a symmetry that the total spin as that total commutes with the Hamiltonian, and so you can only focus on the part on the largest part, that is the one which has, so I have written here one with total spin component to be 0. So I have solved this model for spin of size L equals to 18, but in practice people have solved it for L equals to 24 because you can only focus on one part of the system, and also because this is sparse, so you can use parallel techniques to numerically diagonalize this model.
what is your distribution of this diagonal disorder? 0 to 1.
It's no. So this colored here corresponds to variance, and one actually I have just put here for schematic representation, but it depends upon this. So all of them are Gaussian distributed with some normal distribution with some zero mean and variance H, and we tune this disorder strength H to characterize a.
You said that when you sparse matrix,
Yeah.
like all the they do not interact with all.
Yeah, because we have only nearest neighbor.
Interaction.
Yeah, nearest neighbor. Yeah.
Yes.
Si plus 1. Yeah.
So can you also consider the laziness on this point?
Yeah, maybe, but that was not into my interest.
In that influence your result too much?
Yeah, I don't think so because that will only increase the number of off-diagonal elements, and so maybe the phase transition point will shift, but I don't think the formalism has to change. Thank.
So, could you put the margin was here? One dimensional Heisenberg model should not give you the phase transition.
Okay, so I have only that is so as far as I remember, that takes into account the Landau-Ginzburg theory of phase transition. But for disorder systems, I'm not sure if the same theory is applied because what I have studied that is in terms of Ising model, which is not a disordered model. So whether that model simply applies for disorder systems also, I'm not sure because we very well know that the Anderson transition happens in one dimension for any finite disorder, and because that's a disordered system. And Mervin-Wagner theorem, I'm not sure about it.
Heisenberg model.
For disordered system, Heisenberg model is there, but without disorder, I think, not with disorder. Heisenberg model has only like you consider interaction of all the spin directions, Si, X, Y, and Z. But with this disorder, I don't think that that theorem is applicable. I'm not sure. I could be wrong.
No, one must simply say if you have short range interaction, see only there cannot be any phase transition.
So it doesn't.
The other phase transitions are like washed out, not.
Yes.
Yeah.
Actually not helping to build the order. As you said, equilibrium. POC also equilibrium, right? It is not non-equilibrium.
No, I think this is non-equilibrium because I think this in terms of disorder.
Is there any time is here? No.
No, it's only parametric. Yeah, because a quench disorder system, so there is no time right now here.
Disorder Anderson thing is that it says that any disorder will localize your system.
Yeah. Yeah, so it's a transition from localization to thermalization. So it's about key. So there's no order, it seems, because when we think in the ferromagnetic system, there's an order because all the spins are pointing in one direction or they are not pointing in any direction. But here, what but this transition is about whether your wave function delocalized to the whole space or it is localized to some parts of the space. So how does that correspond to the Mermin-Wagner theorem? How does it applies to this models? I have no idea. Thank you.
Now we have Shogoto Vishwas, a PhD student from our very own Presidency University, Kolkata. Would you like to call him?
না না he just like এটা সাজেশন হবে না Oh. So today I going to discuss one of my research work during my PhD study, complete delocalization of the single particle eigenstate of a class of one-dimensional decorated lattices. It is basically a quantum dynamical study. Before going to details, here is my outline of my presentation. First one is actually in this research where we discuss complete escape from the localization in a class of aperiodic lattices and the corresponding metal to insulator transition, which is defined by some magnetic flux. And then we focused into my main research about the quantum dynamics of a wave packet by calculating mean square displacement, return probability, temporal autocorrelation function, information entropy, as well as the time evolution of the inverse participation ratio. So here, first one is actually a Fibonacci sequence of a diamond stub network, and second one is the Fibonacci sequence of a diamond stub network. Here, each diamond cavity is actually threatened by uniform magnetic flux phi. Now, using a decimation scheme, one can easily decimate out this red color site. Then both of these lattice network are mapped into in such a simple Fibonacci array. So now, due to this decimation process is implemented, hopping integral as well as the on-site potential are renormalized. So now there are some function of energy. And these are actually three different types of atomic sites. One is alpha site between L and L pair. Another is beta site between L and S pair, and other is gamma site between S and L pair. So here is we actually we discuss all of these models using a tight binding formalism, and here is basically we calculate the transfer matrices. This transfer matrices is basically relate the amplitude of the wave function of some psi n or some psi n minus I psi 2 is initial wave function, say psi 1 or psi 2. So using this equation, now we can easily write down the transfer matrices of this alpha and this beta gamma pair. And these are the corresponding transfer matrices. Now, these transfer matrices plays a very important role in controlling the localization and delocalization properties of such decorated lattices. So, this is actually this transfer. It is observed that the transfer matrix of this alpha site and this beta gamma pair is commute independent of energy when this particular situation are achieved. This is basically a numerical correlation between the hopping integral, and another is a particular magnetic flux which is 1/4 flux quantum is implemented in the diamond cavity. So due to this commutation, we can rearrange this whole aperiodically decorated lattices which have no translational order can switch their position and map into their periodic order. And due to this, now these types of aperiodic lattices transmit a complete delocalization. And here we plot the average density of state and corresponding transmission coefficient. And from these two graphs, it is exactly clear that if these decorated lattices which have no transitional invariance, still in this particular situation, and this is actually basically the resonance situation, this lattice geometry is completely transparent to an incoming electron within the allowed energy band. Now we focus in my main discussion, that is basically still now all the research work done in some aperiodically decorated lattices is mainly based on the time independent Schrodinger equation. But time dependent solution of the time dependent Schrodinger equation are equally important. So here, if we put a wave packet at any size of a aperiodically decorated lattices, say at t equal to 0, the corresponding wave function can be written as this form. And if is allowed to move some finite time evolution, the corresponding wave function is can be written as in such a way. Now, here we present the passive distribution of the wave packet for different time instant. So this 2 is actually, when this lambda equal to 2 or phi by phi not equal to 0.25 is basically a resonance condition. And at this condition, it is seen that the wave packet are spread out from its initial site of release at the time close on. And this is actually for the away from the resonance condition. And this particular situation, it is seen that wave packet remain in its initial location after a large time evolution. So this is basically indicate a complete delocalization, and this path is actually indicate a localized or some subdiffusive spreading. Now, there is a question: can we measure this rate of spreading of the wave packet? Answer is yes, using some mean square displacement technique. And here, M is the side where we put initially the wave packet. So between this sigma, this mean square displacement has a power law form given by this equation. This mu is actually the time exponent of the mean square displacement. Now, depending upon these numerical values of this mu, we can classify the whole lattice system in different categories. Say for mu equal to 2, such that the spreading of the wave packet is very high, and at that particular case, system show the ballistic motion. And mu is in between 1 and 2, the system show the super diffusion, and mu is exactly equal to 1, system show diffusive motion. And when mu is between 0 and 1, then there is a very small spreading of the wave packet, and in that case a system classified as a subdiffusive region. And each system in its initial location after a large time evolution, then we can say that the system is completely localized in phase. So here we calculate the mean square displacement for two different aperiodically decorated lattices. This is diamond stab lattices, and this is a diamond stab lattices. So this is actually for the resonance condition marked by the red color, and that is as lambda equal to 2. So at this particular situation, the MSD varies as t square, which indicate the system is completely delocalized. So at this particular situation, as the resonance condition is achieved, all the eigenstates become delocalized. And further, if we increase the lambda, say 3.5, so it is we deviate from the resonance condition, and at this particular situation, the time exponent goes as less than 1. So it is indicate a system is under subdiffusive region. And this one is for the diamond stab network. At this particular situation, we vary the magnetic flux. When flux is 1/4 flux quantum, system is completely shows the ballistic motion marked by the red color. But when a magnetic flux is applied, is half flux quantum. At that particular case, the system shows dependence with time is completely to the power 0. So basically, no dependence with the time, which suggests that system remains in its initial site of release after a large time evolution. So it is the complete localized case. And this is the graph for the time exponent versus lambda. From this graph, it is clearly seen that when lambda equal to 0, system in the super diffusive region. And further, if we tune the lambda equal to 2, system achieve the resonance condition, and corresponding time exponent is exactly equal to 2. The system in its ballistic motion. If we further increase the lambda, system moves to its subdiffusive region. And another presentation, this is actually for the different values of magnetic flux. When no flux applied, the system is under super diffusive motion. Further, we increase the magnetic value, magnetic flux value. Then at 1/4 flux quantum, this shows the ballistic motion.
And if we further tune the magnetic flux, say half flux quantum, the exponent is completely zero. So there is a transition from a metallic phase to insulating phase via superdiffusive, ordinary diffusive, and subdiffusive phase. So magnetic flux event, metal to insulator phase transition is confirmed again. And there is another interesting thing, which is basically the return probability. So what is the return probability? Return probability is that, say if we put a wave packet in a particular site in some decorated lattices, now if I calculate the amplitude of the wave function at that site after a large time evolution, then what happened? Then if we get for the delocalized phase, the return probability is basically zero. Then these two actually for the delocalized phase at the resonance condition, it's mean if as time goes on, the wave packet spread out from its initial location. So there is basically no return probability as time goes on. And this panel is actually for the subdiffusive and localized phase. And at these two sides, it is clear that system contain some finite return probability. So it can return in its initial site of location after a large time evolution. And this is for the subdiffusive region. There is a small decay, and this is for the completely localized region. Okay. Oh, yeah. And another observation is the temporal autocorrelation function. This is basically the time average of the return probability. And this here also this CT is a time dependence. Is for a completely delocalized phase, it goes as t to the power -1, and a completely localized phase it goes as t to the power 0. And this is corresponding to the two different network. First one is the Diamond-Stab network, and second one is the Diamond-Stab network. Here also the delocalized and localized phases are confirmed again. And this is the most important thing. This is information entropy, which is a very popular measurement to detect localization and delocalization. Here, Pn is actually the probability of finding particle at some instant. And this show actually for the delocalized phase when the system achieves resonance condition. So here is a monotonically increasing of the information entropy with time, and then followed by saturation. And if we increase the system size, this saturation is also increased. This saturation means the wave packet already spread out all over the system. No further spreading is allowed. So if we see the increase the system size, corresponding saturation is also increased, which confirms the system is delocalized phase. And these two for the subdiffusive and the localized phase, here the rapid saturation of the information entropy with time is observed. And it is the last one. Here we calculate the inverse participation ratio as a function of time. Inverse participation ratio basically measure localization and delocalization. Is basically measure the participation of the wave function with neighbor size. So for a completely delocalized state is termed as 0, and completely localized state is goes to 1. Here the time dependence are shown. This is for the Diamond-Stab network. Here, this red color is for the delocalized phase, is goes to 0 as time flows on, and these two actually for the diffusive and subdiffusive region is goes to 0 after a large time evolution. And this is for the localized phase. So here, this blue color curve indicates that when the system is a completely localized phase, the IPR never goes to 0. Is always contain a finite value. So all these one is not only applicable for the Fibonacci sequence, it is also applicable of the other aperiodic sequences such as silver mean or copper mean ratios. So these are my references. Here is my acknowledgement to my supervisor, Professor Onova Chakraborty, and Sir Professor Mukti Acharya, and my senior research colleague. Thank you.
So in that diamond star case, why you consider the star? Because even without the star, you can do. Is it just to make symmetry, like symmetry so same way like a figure AM? Because even without the star in figure B, you could have a resonance condition.
Yes.
So then why you took the star? Because if you took the star, then you need an additional value of flux also. Both the conditions you have to satisfy, or even without the
Actually, we similar formalism.
same equation and same similar formalism that we construct these lectures.
Yeah, that in the start, you say second figure B, even if you do not put the star, then your life becomes more simple actually. You only need to satisfy one condition, not the both the conditions simultaneously. You do not need a 5. Even without 5,
Yes, yes, that also.
Just with an edit on what this fluence you need the flux. Like flux is something that you can offer from outside. The moment you remove the flux, remove the star, you have to design one lattice under another to see change conditions. Okay, they will all be resonance under different conditions. But here what he does, I believe, if I'm not wrong, that if you fix one side for all, the relative values of Hawking parameters, then you have only one changes with what you do in the magnetic class. Continue to get the relevance.
So now I got
That is a single system.
Yeah, so now you once you build the system, then there is an
Yes,
external parameter by which you
one
can
system. Okay.
So can you please go to the slide number 10?
Yes.
Yeah, so in slide last figure, U versus 5. Why you have the, can you tell me why you have the similar symmetry on the other side also?
Oh, that is because
See, it comes down again, it picks up. Why with the symmetry?
this is because the resonance condition is achieved 1/4 flux quantum, 3/4 flux quantum, and so on.
Why? That is my question. Why? Why you are getting back?
Oh, okay. That is from the resonance condition. I can show you. And this is actually a resonance condition. If we put phi equal to 1/4 or 3/4 flux quantum and so on, the resonance condition is satisfied.
There is a kind of physical interpretation that suppose why you are not taking back on say 0.5, 5 not by 5 by 5 not equal to half. Why you are getting back at 3/4? Why you are getting back at 3/4? There is a connection 1/4 to 3/4. It's because of the periodicity of the class. I think. So another last question is that.
Oh, actually, this is a zero flux and
Like when you one of the slides, it showed some deviation from the resonance condition. What is the percentage of deviation by which you can maximize the localization?
okay.
Suppose you deviate a lot, then automatically you will localize. But what is the minimum deviation by which you can achieve?
Actually, for first case, we did not achieve the
Can you
localization.
go to the picture that yeah, this one. What is this deviation? So here I can see that you have deviated 100%. Right?
After when the
0.25 to 0.5 is 100%.
okay, this is actually resonance condition, and this is actually a time.
Yeah.
This is for a time t.
Like 100% deviation. 100% deviation. Right?
Okay, after that, there are saturation condition are achieved when the wave packet move all over the system.
Deviate by say 30%. Then still you will get similar picture, or you will have some spreading of the function. Suppose if you put say 5 by 5 not equal to 0.3.
Oh, no, that is completely other. The rate of spreading of the wave packet is completely different from that.
It will not depend on the response.
Resonance condition is phi equal to 1/4 flux quantum.
Yeah, so that's what my question is. How much you have to deviate from the resonance condition? 100% or say even 50% deviation if you do, till the packets will be localized.
For the it is localized only at the half flux, otherwise half flux.
Oh, otherwise no.
No. Otherwise, it is under other regions, say super diffusive, sub diffusive, ordinary diffusive.
So if you also deviate say by 30%, then you have
some diffusive nature or either super. Complete localized only observe at half flux one.
Is the formula to get this inverse participation ratio formula?
Formalism. That is actually psi to the power 4, where psi is the normalized wave function.
So why it is 4?
Why it is 4 to the power? Okay. Wait. This is because if a system is completely localized, if we put some initial site, it has no participation to the other site. So if we calculate the psi to the power t for the all system size is at particular position is 1 and all other position is 0. So IPR for a localized state always comes to a finite value very close to 1. For a delocalized phase, the wave packet spread out all over the system or distributed all over the system, but their amplitude are quite small because they satisfying the probability of all sum is exactly equal to 1. And if we calculate just psi to the power 4, it is more and more smaller. So total summation is goes to 0 when the system is infinitely large.
So then it's will count from the bottom number close or top bottom number. And you are saying that to what to say, match the probability which you are getting. So taking it as four, but not getting it through the formalism way like doing the maths and then okay, getting the answer and it will be satisfied as rather you say that first you are taking the probabilities and then applying the one can to the power for getting the best approximation for that. And you there are some details on that.
No, basically, if we focus on the formula, it is basically summation of psi to the power 4 by the normalization of the wave packet psi square by to the power whole square. This is actually the formula. And from this formula, we calculated this.
Okay, thank you. Psi to the power 2x. So this is IPR 2. Yeah,
Actually, this psi is the moment. This 4 is the moment, actually. And
Reverse participation
and
in general, two and like you have used IPR.
2 yeah, this is actually this particular case is equal to 2.
Yeah, that's what.
Other if we focus on the multifactoriality or other distribution, then we set other values of it. Yeah.
Okay, so wait, this one. Yeah, you question 10. You
Equation 10.
Equation 10, yeah, that's C of T.
Okay.
Correlation function.
Okay, yes.
Trying to normally correlation functions are defined at two different times, right? Here it's not. So why do you call it correlation function?
Okay. Here is actually also two different time. It is from 0 to t. If we initially put the wave packet at t equal to 0, then if we find the coming back to its initial site, and this is actually the return probability. And here is actually time average of the return probability. And this is the temporal autocorrelation function.
It just gives you how it spreads with time, right?
Yeah. Now this is measure. This is measure if we put a wave packet at the initial site, what is the probability of the particle at that site after last time evolution? And spreading is measured given that given time is 8. Spreading is measured by the mean square displacement. That I have already said.
Thank you, Mr. Shogoto Vishwas. Last but not the least, we have a last speaker, Vyash Mukherjee, a PhD scholar from Shah Institute of Nuclear Physics, Kolkata. I would like to call on stage. Pointing, major pointing, and from here, and from here you are clearing it. So, which Good afternoon, everyone. So my topic is a bit different from other speakers. It's of synthetic biology. So it is genetically engineered bacterial computer identifies prime numbers, perfect power numbers, and connected hard graph.
So first, let us delve into the background of living cell-based computations. So the first living cell-based computation that was developed was of a synthetic genetic toggle switch, a repressilator and oscillator. And later, different types of synthetic genetic models came up, such as half adder, full adder, analog to digital converter, multiplexers, demultiplexers, and whatnot. Uh, Even abstract computational problems were also developed using living cells. Classic example of that is the maze problem solving by bacterial cells. So this is from our lab itself. There are two more instances where living cells were used to show abstract computational problems. But the problem is that no one has ventured into the decision making computational problem solving yet. So, my work mainly focuses on that. So, what is a classical decision making problem? It's very simple. It's having a yes or a no as an output. So if we ask the question if five is a five a prime number, so for that we have either a yes or a no as an answer. So in this case, it's always a yes. We know five is a prime number. But does a computer know if five is a prime number or not? So for that, different types of programming languages have been made for the computer to uh, ease our task. So this is a Python programming language for identification of prime numbers. It has mainly three parts. Firstly, the part where we give an input or the number, and then the second part where it consists of the predefined set of rules or the algorithm that the computer processes to give us the third part, which is the output that is printed as yes or a no. So our question is, can engineered living bacteria solve these decision-making problems? So the answer is yes. Engineered living bacteria, we have actually synthesized these genetically engineered bacterial computer that can tell any number from 0 to 9 if they are prime or not a prime number. So imagine a bacteria can't even identify a prime number. So we have to pose the problem to the bacteria in such a way that it understands our question. So for that, what we did is we converted all the decimal numbers from 0 to 9 into their binary counterparts. So these are called bits, first, second, third, fourth. So each of them are converted into their corresponding binary bits. And then what we did is we assigned each of this bit column with a particular chemical inducer. Like this first bit column was assigned the chemical inducer was AHL. The second one was ATC, IPTG, and arabinose. Secondly, what we did is for 0, we assigned them that the particular inducer will be absent in that culture media. And for 1, it represents that that particular inducer will be present in the culture media. So if we want to ask this genetically engineered bacterial computer, which consists of a heterogeneous mixture of different synthetically, genetically modified bacteria, uh, if you want to ask the question if 5 a prime number or not, we'll add simply IPTG and AHL and not add arabinose and ATC to that media. And this will then process and give us our output result. So here we assigned E2 crimson or the red fluorescent protein to be to tell us the output that it is no, not a prime number, and EGFP or the green fluorescent protein to be yes, it is a prime number. So if we check for 5, it is actually glowing green. So we can tell that it is successfully identifying prime numbers. So if you check for all the numbers, it has successfully identified each of them. Now the question arises is how do we engineer these bacterial cells to identify prime numbers? The simple one-liner answer to this is by creating neuromorphic computer with bacterial cells. So, like we have neurons, the functional and the structural unit of our brain. We have here what we have is vector neurons, bacterial neurons. So they like neurons process the chemical inputs or the impulses from a previous neuron and process it and give us an output. Similarly, this vector neural network also processes our chemical inputs or the inducers and with the help of the synthetic genetic circuits that are present within them, it processes it and give us a different set of output results. So that this input and output relation actually mimics that of a artificial neurosynapse activation unit function. So this is the activation unit function where O represents the, for a particular vector neuron, O represents the output fluorescence of that vector neuron. And it is 1 by 1 plus e to the power w1x1, w2x2, and so on, you go on, plus b, where w represents the weight of each of the vector neuron, and x represents the concentration of each of the input inducers, and b the bias of each of the vector neurons. Also we actually create this synthetic genetic network inside each of these vector neurons using the weight signs that we get from this activation unit function. So plus represents a gene activation, minus a gene repression, and 0, which means insensitive to gene regulation. So how do we map our prime number identification problem in ANN? So as I discussed earlier, this is the input matrix that we generated to pose the question to our bacterial computer. And this is the output matrix, which is the desired output results that we are supposed to get from this bacterial computer. So with this input and the output matrix, we mapped this artificial neural network type of schematic diagram. So to understand it further, let us focus on this one, this vector neuron ACE8. So here, as we can see that vector neuron ACE8 has a positive weight sign for X1 and X2, but not for X3. This means that this X1 and X2 both simultaneously activate this vector neuron. Here X1 is AHL and X2 is IPTG. So for this, how did we genetically engineer this vector neuron? Is we constructed this synthetic promoter that has an IPTG, a lac repressor binding site and a Luxar binding site. So whenever we give IPTG and AHL both in the culture media, they actually the Luxar and the repressor that is present is moved from the promoter region, and the RNA polymerase can actually sit on this promoter and EGFP glows. So this circuit is activated. And further, what we did is we characterized this vector neuron ACE8 with doses of input inducers, AHL and IPTG. As you can see that with the saturated amount of AHL and IPTG both, then only we get the maximum normalized fluorescence in this case. And then what we did was further validate this by dose response experiments where we took an ascending increase in concentration of AHL and IPTG both, and we saw an increase in normalized fluorescence in a log sigmoid fashion. Then we calculated the weight and bias and other parameters from these dose response experiments, and we put those in this equation, the activation unit equation, and we generated this 3D simulation curve, a graph, where we plotted 50 concentration points of AHL and IPTG both in X and Y axis, and we validated this simulation result experimentally with 13 concentration points. And as we can see that we got a very similar result to the simulation result experimentally too. Yeah, sure. So these are the other vector neurons that were used for this prime number identifier. Similarly, the design, characterization, dose response, and simulation and validation experiments were done for each of them. Now, the second part was creating a perfect power number identifier, similar to the prime number identifier. Here also, we generated this input matrix to pose the problem and the output matrix. These are the 4 vector neurons that were required for this perfect power number identifier, 9, 11, 6, and 10. And these are the optimized results for each of them. And you can see from this macroscopic results that each of these perfect power numbers were identified correctly. Similarly, another example is also shown that of if n is a connected high graph number or not. And these are the constituent vector neurons, the results of each of them. So to summarize, here we showed 3 problem-solving yes or no type computations by our bacterial cell-based computers. Each problems were posed with the help of chemical inducers that affect the genetically modified vector neurons, such that they release an output chemical as an answer to the problem. The problem is posed in binary 0 or 1 that corresponds to absence and presence of chemical inducers respectively. The output chemicals are fluorescent protein, CGFP, and E2 for answers yes and no to the problem respectively. But for perfect power numbers, we actually changed the output a bit. We assigned E2 for yes and EGFP for no. And also, I would like to mention that vector neuron ACE8 and many other vector neuron actually was used in both prime number identifier and connected high graph number identifier. So if we have a library of these vector neurons, we can actually mix and match each of these vector neurons like Legos, and we can create different functions. So this shows the modularity of our system, and hence we demonstrated the abstract computational decision-making problems can be solved by genetically modified bacteria by neuromorphic computing. And I would like to thank my supervisor, Dr. Shongram Bag, my fellow lab members, and my seniors. And I would like to thank the organizers and the CMMSSP this conference for giving me this opportunity to present my work. Thank you so much. Take some questions now.
So, thank you for the talk. I have a quick question that how much time it takes to identify you are giving only one digit prime number. So how much time it takes? Because in Python it's in milliseconds.
Yes, absolutely right. You are absolutely right. So if we don't need to compare it with actually a computer, because bacterial cells itself is a living system. So decision making problems, these bacterial cells can solve decision making problems in living systems very easily that computers can't. Like if you think about a therapeutic, suppose the bacterial cell can go inside the body and can decide for itself if there is a need of any type of chemical to be released or not in that case. And if you consider a system, an environment where suppose pollution level is increasing, like CO2 indicator. So for a particular concentration level, that bacteria will decide for itself that the concentration level has increased to a certain amount, and it can then release certain fluorescence or any type of chemical to let us know that CO2 level has increased. So another advantage of using bacterial system is that bacterial system is in micron scale. So it's very so the if I'm correct, the smallest computer chip, I think it is of 1 millimeter cross 1 millimeter in area. But bacterial cells can go up to in micron scales, as I've mentioned. So, yeah, this is a proof of principle concept, obviously, and you can actually
I have a very basic writing understanding. You have converted the numbers to binary numbers, right?
Yes.
And one binary numbers is pigmented to some pigment. It's actually some pigments,
Mhm.
different colors.
No, no, not pigments. Each of these binary bits corresponds to presence or absence of a particular chemical inducer that we give to that culture media.
So
Yeah.
there is 7 is a prime number,
Yes.
6 is also a prime number.
Yes.
So both means these different colors of chemical, right? Am I right?
No, prime number. All the prime numbers will be identified as a green. Yeah.
Inducers are different. Quite nice stuff. I just had a question about the fitting that you had,
Yes.
because if you look at the weights that you are calculating,
Yes.
it seems that you can, there's so many of them that you can have anything, right? I mean, in the fitting process, for instance,
Yes.
with the form that you are having, I can put a multitude of possibilities to give you the same plot. Isn't that correct? I mean, because
Actually,
you're not pulling out one by one. Let's say you have a simpler form by just taking out something which is not there and then looking at it.
yeah, yes, we have simulated this, but we have also we have actually experimentally validated each of them. So with different weight and bias values that we have calculated for this, we have actually optimized the results in such a way where we get a correct log sigmoid graph or a optimum fluorescence value. In that case, we have optimized the saturation points of each of these fluorescence also. So
how do you control the weights in the experiment?
uh, control the weights as in we have actually um, we have actually experimentally we did sort of from the simulation results we have experimentally seen that where the log sigmoid curve is actually taking place. So for example for weight values for IPTG, we have seen a weight value of 5 or lesser than 10. We have seen this log sigmoid curve has not gone up after this. So from there, we actually optimize the values and we.
Yeah, and the next question is, where does the genetic said genetically modified bacteria? So I
Yes.
think why that was required? I mean, normal bacteria would not function.
Yeah, normal bacteria can't even it won't take up IPTG or
Oh, I see.
ATC or HL unless we modify the genetic circuits inside them.
So I have this very basic question. So for very large number, so the current available most optimized programs are what has order of log time complexity. So in your case, is the time complexity is lesser or greater?
Time,
You will time complexity. So in which order of magnitude of time does your system is taking?
okay, so this is a living system, obviously, and it takes approximately 10 to 12 hours to get an optimum fluorescence saturation value.
So the another question is very great. So as you know that demand hypothesis has some connection with prime numbers. So are you feeling that your computer can in future may solve this demand hypothesis with some real price problem currently?
Yes, you may, you may solve that. This is a proof of principle concept, so you can take this concept and you can build onto it. Like you can actually, we didn't show here, but we can go up to, this is up to 9. You can go up to hundreds, even thousands. And for that, you need a lot of number of inducers, orthogonal diffusible chemicals, and also different huge number of layers also. This is a single layer artificial neural network. You need a lot of different layers for that. So thank you.
If I understood correctly, for each operation, like finding prime number or the other thing, you need a different genetic circuit, right?
Yes, different genetic circuits.
That means one cannot do like computer can, that is not possible here.
No,
In operations, you need different genetic circuit.
yes, a mix and match of different genetic circuits for each of the function. Like this component is 8 can be present in both prime number identifier and even connected high graph identifier. So what we are doing is we are focusing on building a library of these vector neurons so that we can mix and match different vector neurons here and there, and we can solve this in and map. We can
So circuit is basically implementing a truth table, right? Directly.
yes,
Like this green and red.
yes,
It's not actually combining like a normal computer does.
no,
You know the results that for these green inputs, I should rather for these inputs I should have this thing.
yes,
The final
yes,
result.
yes.
That's a smart one, right? Ah,
Thank you, thank you.
Thank you. We appreciate your participation. And thank you to the audience for your engagement. With this, we conclude our third oral presentation session of our 2-day national conference. I will now hand over the mic to Shafi.
So thank you, Vishika. Now it's time for the lunch break, and everyone is requested to take your food packet from outside. So we will also have the poster presentation session in the meantime. So all the participants are requested to take their position in front of their posters. So we will meet here again at 2:30 p.m.